Okay.
right now.
Okay. Yeah, Matias, please go forward.
Great. So thanks very much for the opportunity to speak here. I'll talk about various things related to the events that LIGO has detected. As some of you might know, I've been working for some time now on LIGO related things, and with a group here, we've reanalyzed the public LIGO data and we found some more events. So I'll tell you a little bit about that, but not too much, because after our work, the LIGO has released many more data from a new run, the observing run 3. And I think it's more interesting to just discuss what we know at the current time. And at some point in the middle, I will use it some excuse to tell you a little bit about what we did during with the data of observings 1 and 2. We haven't yet done the equivalent thing for observing run 3 because the data is not yet public. So they've released little chunks of data around individual events that they found, but they did not give out the entire data set for other people to either find new events or assess the significance of the events that they found in an independent way. So let's see. Okay, so these are various people that are involved in this work here at the IIS. People in the top row are the ones with which we analyzed the 01 and 02 data, and newer people at the bottom, Hong Sheng and Seth Olsen, now are joined the group. So both Seth and Javier are students. Okay, so as I said, I will just do some brief introduction so that we are all on the same page. Then I'll spend most of my time talking about the current status of the observations. What are the outstanding questions, things like that. Maybe in the middle of that, as I said, I will use some excuse to tell you a little bit about what we did. Then I have some more slides about our search and so on, but most probably I will not get there. And people, of course, if you want to ask me, I'm happy to spend as much time as you want, but it might not be as interesting. Okay, so just to get everybody on the same page, I'm going to talk about gravitational waves. Of course, they come in many frequencies, and they're produced by different sources, and they can be detected in different ways. And this talk is about ground-based detection of gravitational waves. They typically have frequencies about 100 hertz, give or take, so 1 decade in another direction, and they are detected. They are produced by neutron star binaries, black hole binaries that merge, and we catch them, and these frequencies corresponds to the end of, or the last parts of the inspiral, and then eventually when they merge. So as I said, they are produced by binary systems. As you know, when the binary is close enough, it emits gravitational waves, it loses energy. The distance between the two stars or compact objects shrinks a little bit, the period decreases, so the frequency increases. And so you get this chirping signal. So the plot at the bottom left is an example of the gravitational wave signal as a function of time, and the frequency is increasing, the amplitude is increasing as well until you get to the merger. The parameter that describes this chirping behavior is a combination of these masses called the chirp mass. So in this binary system, perhaps the two masses, we call them N1 and M2. There's a total mass M. There's a mass ratio, M1 and M2, M1 over M2, say. There's a symmetric mass ratio. These are all things the people use to characterize the binary, and the frequency, the time evolution of the frequency is given by this formula there, where it's a certain time dependence, and what sets this the scaling of this time dependence is the so-called chip mass. And on the bottom right, you see the amplitude as a function of the frequency of the gravitational wave. So if you Fourier transform the plot on the left and you plot the modulus of the Fourier transform, So as a function of frequency during the in spiral phase, which is the beginning of this plot, so at lower frequencies, the amplitude scales like a power law with an exponent frequency to the -7/6, which you can easily get from simple arguments and the quadrupole formula, things like that, until you get to a maximum frequency corresponding to basically the Schwarzschild radius of the combined black hole. And so for a 50 solar mass total mass, this is around 100 hertz, and then the signal dies, so the Fourier transform drops very quickly. And then the place of this cut gives you a sense, or allows you to measure the mass of the combined mass of the system. The evolution in frequency lets you get the Chirp mass. From this, you can estimate the mass ratio, for example. As the mass becomes smaller, the frequency, the maximum frequency becomes higher. So this plot on the top, on the bottom right, just moves to the right. Eventually, for example, if you were to, so LIGO is sensitive to frequencies between 20 hertz, say, and a little bit below 1,000 hertz. And by the time you get to a neutron star binary merger, the maximum frequency falls outside of the band of LIGO, just to have a sense. Okay, so I mean, you can try to, I could try to give you a little bit more formulas at the end of the day for the binary black hole mergers that I will be discussing, and for which LIGO has detected most of the events. These simple post-Newtonian formulas are not very applicable because we only see the final parts of the merger, and so the formulas for the waveform are some combination of these post-Newtonian formulas with numerical relativity and so on, as you know. But just to give you some sense, so if you were to try to model in the post-Newtonian expansion regime, this Fourier transform of so h of f, the Fourier transform of the waveform, it would have an amplitude which was plotted in the previous slide, that went like f to the -7/6. It would have a phase, and if you look at the phase, you can in powers of v over c, which can be translated directly into powers of the frequency. X is the frequency over some fiducial frequency. So each order in the post-Newtonian expansion has some different frequency dependence. The lowest order is just given by the Chirp mass. So there's a bunch of parameters here. All I want you to get from this, that as you at the lowest order in the post-Newtonian expansion, the frequency dependence of this Fourier transform just depends on this curly m, which is this Chirp mass. As you go one more order, the mass ratio, which is this eta here, starts coming in. Then next order, beta, which is the components of the spins of the black hole in the direction of the orbit. So the spin orbit coupling type term comes in. Next order, you get the other components of the spin and so on. So if you were to be able to measure this with very good accuracy and be able to distinguish the coefficients in front of these different frequency dependencies, you will be able to start getting all of the parameters of the binary, which naively there is just, the intrinsic parameters of the binary are just the two masses and the three components of the spin of the two black holes. Say I'm talking about a black hole binary. Then there's a bunch of other parameters that are about where the binary is at on the sky, the distance, the inclination of the orbit, the time of the merger. So there's a bunch of other, let's say, extrinsic silly parameters that are just about how I'm observing it, but they add up to quite a few parameters. So now, at the current time, with the observations that we have, for the most part, if you look at the typical example of these binary black holes, we are able to measure some Chirp mass, say, very well. The mass ratio not so good. The component of the spin in the direction of the orbit and the mass ratio are these are the two things that are more or less good, well measured. After that, not very good. So other components of the spin, not very good. These other components in the plane of the orbit lead to precession of the orbit, effects that eventually, in addition to this phase shift that is here, there's also some precession of the orbit and so on. All of these things, eventually one should be able to observe. And in some of these events, there are hints of these things, but for the most part, we're stuck with just a mass, pretty well measured, an overall mass scale, and a mass ratio and a spin in the component of the angular momentum. So L dot S, and just this would be two numbers, just the projection of the spin of each of the black holes in the direction of the angular momentum. But in reality, we can just measure a weighted average of these two numbers, weighted by the mass of the black holes. This is what people call the sky effective, which is, the Z in this formula is the direction of the angular momentum. So we can measure the weighted average of this Z component of the spins of the black holes, weighted by the mass. So that's where we are at in terms of parameters for individual systems. This is just a little compilation of all the first events. What is plotted here is on the curve is examples of these waveforms that fit the data of the individual events. The image on the back is some sort of representation of the power in the signal as a function of time and frequency. X-axis is time, Y-axis is frequency. All I want you to get from these figures to look at the scales in the X-axis and see that, and the length of these different waveforms. The length there that is plotted is the time in which the frequencies are of the emission is in the range that LIGO can see. So you can see that the length of each of the events are equivalently at the number of cycles that LIGO can see is different. So for less massive things like the binary neutron star, it is there in the detector for many tens of seconds, and it does a humongous number of orbits. For the very heavy guys like the first one in the plot there, it's just a few cycles. So obviously also how well you can constrain parameters. If you just see a few cycles, it's very different than when you see a much longer signal. So not just the signal to noise is important, but also the parameters of the system determine how much information you can actually extract. And we might hope to learn from these observations, maybe properties of these black holes and neutron star populations. Maybe some people want to test whether the solutions, black hole solutions, are the ones that GR tells us that they should be. And from most directly, what we will learn is about the processes that form these black holes and the black hole binary. So I'm mainly going to talk about the black hole mergers, because those are all of, except for one and perhaps another one, which might be a neutron star black hole merger. Most of these 50 events that LIGO has are binary black holes. So I'm mostly going to talk about that. Okay, great. So what is the status of the observations at the current time? So as you know, LIGO went to some upgrade from its initial LIGO to what is called this advanced LIGO that increased a lot the volume up to which they could observe events. And after this advanced LIGO, it has gone through a bunch of upgrades. So the original discovery was during what was called observing run 1. Then came observing run 2, and now we are in observing run 3. And data from the first half of observing run 3 has been released. What has been released, as I said, is just the catalog of the things that LIGO has found in that observing run. So the plot on the bottom, the plot on the bottom left just gives you some sense of the increase in the range to which they can see a binary neutron star. But maybe as a figure of merit, you can see the ratios of these things as how things are being improved between the different observing runs. And on the bottom right, you can see just the cumulative number of events that they have reported, and you can see that the catalog at the current time has around 50 events, most of which came during the first half of observing run 3. This is called observing run 3A. And so we had reanalyzed observing runs 1 and 2. We had found additional events that more or less they were almost the same number as LIGO had reported, which are the only ones that are quoted in this slide. But this still is dwarfed by the new events. It's still a small number. But in any case, I'll show you some examples that might be interesting. So highlights from '01, well, of course, just the discovery of it, and so everybody was very happy. From observing run 2, the binary neutron star came along, and okay, it was followed up all kinds of. It had an electromagnetic counterpart. It was used to, determine the speed of propagation of the gravitational waves, as well as properties of the ejecta of these explosions and the metals that are produced, or the heavy elements that are produced, etc. So, okay, what about observing run 3? So now in observing run 3, I think the main thing is the fact that we now have many, many more events. So we can start to ask better questions about the population, the origin of these black holes, and then the black hole binary. So the two questions are, the origin of these black holes, most probably, they are the result of stellar evolution of massive stars, but there's several puzzles related to that I will tell you about. And you can see these are just the list of all the events that LIGO reported in observing run 3 by itself. So just as a way of seeing things, so these gravitational wave events, their names are usually GW and then a date. Anybody that's GW 19 something or other, it comes from observing run 3. Anybody that is GW 17 something something comes from observing run 2. Anybody that's GW 15 something something comes from observing run 1. So these are all from observing run 3. And what is plotted in this little plot is like the distribution of various parameters of the binary. So the mass of the heavier object is called M1. The mass of the second one, the lighter one, is called M2. Q is the mass ratio. Chi effective is the spin parameter, then the distance. So and so what people have been trying to do is try to, on the basis of these events, try to see if there are patterns, if there's some unusual things, etc. So where do we stand related to that? So I think from the very beginning, from the results of observing run 1, you might have heard, and it's clear that the first thing that people noticed is that the black holes that LIGO is observing are heavier than the black holes that people had observed in X-ray binaries in our galaxy and nearby. So black holes which have a companion and are accreting material from this companion, they emit X-rays. You can find them. You can see the binary, try to get, from the motion of the two stars, constrains the masses and so on. Also the emission of this accretion disk, and etc. And then you get estimates from the mass and the spins of these black holes. And I think the maximum mass of any of those systems was around of the black holes in any of those systems was around 15 solar masses. And I think the vast majority of the LIGO events are heavier than that. And also there was an indication that the few systems that had in the binaries, X-ray binaries, that had a massive star as a companion, that after some evolution might end up being a binary black hole themselves. So the black hole you see and the black hole produced by the death of the second star that is now at the current time is just feeding the black hole that you see, and it's emitting X-rays. Though those heavy ones seem to be spinning. So people try to determine the mass and the spin of these black holes. So the masses were at most 15 solar masses or so, and they seem to be spinning rather rapidly. Not too many examples, as there's the little plot on the right. There are some examples there, but So the sample was not very big, but that was the overall conclusion. And the typical models that people built um, of the masses of black holes were tuned to have masses up to 15 solar masses. So even though stars that end producing these black holes have masses that are much heavier than that, the stars are these very massive stars have very large mass loss. Their envelopes are for example, the radiation from the core eventually the stars become giant. The envelopes are not very bound to the cores, and they lose most of their mass. And so all of the parameters of this astrophysical modeling were tuned so that the masses of the black holes look like the masses that people have found in X-ray binaries, and suddenly didn't work out with respect to the ones that LIGO had seen. I mean, either you can think that it didn't work out, or you can think that in these models, one of the parameters was the dependence on this wind on the amount of heavy elements of the star. The reason for there being or people to expect a dependence on this amount of mass loss on the amount of heavy metals in the envelope of the star is that if you have heavy metals, there's a much more lines in the spectrum of the absorption of the material, and so you can so these stars have a lot of radiation pressure that then gets absorbed by the envelope, and that is drives this wind. And so if you have more lines, more absorption, so there is some assumed or thought to be true dependence that the more metallicity that the star has, the bigger the wind and the more the mass loss. And so another way would be a conclusion that LIGO black holes were produced in environments with low metallicity. So very different from the Milky Way. So you could hang on to your predictions by just making sure that somehow, for some reason, all of these LIGO black holes, very heavy ones, they are produced in very low metallicity environments. So, something along those lines. I think anyway. So that's kind of one thing that people concluded from these observations. I think the situation is a little bit more interesting. That is very complicated modeling. The amount of mass that the black hole eventually has based, let's say you start with a star with a given mass when it starts its life. So this is a plot from a paper, one of the LIGO papers during the observing run 2. So if you look at the plot on the left, so the one that has the various lines, the x-axis is the mass of the star when it starts its life, and on the y-axis this is the mass of the compact object, the black hole that results from, or black hole or neutron star that results from the star, and the lines are various models. Okay, and what you can see is that so there are two gray areas. Those gray areas are the so-called mass gaps. So if you start from the left, you see that you start as you increase the mass of the star, you produce at the beginning below the first gray region. That's neutron stars. You produce neutron stars of more and more mass. Eventually, you don't produce a neutron star, you don't have the explosion, so the supernovae explosion, and all of the mass that is usually driving out of the star during the supernovae explosion falls back into a black hole, and when you cannot form this neutron star. And so naively, or people think that once you cross this threshold in which you don't have this explosion anymore, you start producing black holes, but they start at they're heavier than the neutron star. So because all of this mass is not thrown out, but some of it comes back comes back in to form the black hole. And so that's the reason that there is a gap between the mass of the heaviest neutron star and the mass of the, so people believe, so the mass of the lightest black hole. So this is one of these mass gaps. And eventually maybe more interesting as you continue to consider heavier and heavier stars, eventually what happens is that in the core of the star, if it has become hot enough, dense enough, you can start producing electron-positron pairs. So these stars have a lot, they're supported by radiation pressure, but once the mass becomes large enough, you can start producing pairs, and you're using a lot of the energy now you're wasting it in producing these pairs. You lose pressure support, and bad things start to happen. The star eventually explodes. They have some instability, eventually explode, and so you end up with no black hole. So that's the reason why these curves stop going up, and you don't produce black holes of masses heavier than somewhere around 40 something solar masses. That's the expectation, because the stars that would have produced such heavy black holes are so heavy that in their cores, before you get to the final stages that will lead to the black hole formation and so on, before that time, you start producing pairs, and an instability occurs, and eventually an explosion occurs. You don't produce the compact object anymore. So there was this prediction that there should be, that the black holes would come in, there is a range for them, and you shouldn't see, for example, any black holes heavier than these 40 something solar masses. And this did not quite depend too much on metallicity or anything like that. So people that did these calculations, they're pretty model independent. This cutoff of the maximum mass that you expected to have a black hole. And on the left, on the most left plot, there are all the events that were reported by LIGO. This is a LIGO paper in the O2. And you can see that all of them lie below this green line of the more or less cutoff. Perhaps the heaviest one, 1707.29, maybe a little bit above this number, but it was consistent with it. So these pictures seem to hang together until that time. And if you looked at those papers at the time, they would advocate that, oh, we're seeing this, it makes some sense. This changed when O3 happened, because there are several events that, so you can see here posterior, so the constraints on the mass of the heavier object of various events that are above. I put some vertical line where the maximum possible supposed black hole mass could be due to this pair instability supernovae. And you can see several, in the plot of 4 examples of systems, and the names are there, that clearly are on the other side of this line. The one that sits kind of in the middle, that one is the heaviest one in O2, 1707.29, that I mentioned before. If you look at the names of this system, you will see that 3 of them, so in the label there, 1905-19, 1907-06, 1906-02, these are all O3 events, so are new ones. But then there's also 1708-17. That one is one that we found. So in our catalog, there was already something above this cut.
Sorry, Matias,
yeah.
Can I just ask an obvious question? You're probably going to get there, but this line of the theoretical threshold is drawn very sharply. But what's the leading source of theoretical error, and how broad is that error?
Yeah. So well, you can see. So here the dashed part here is some sort of estimate of the theoretical error. You can see that, okay, there's some dependence on the metallicity of the star, but you have several examples there of calculations with different metallicities. and you know,
So just to lay it out for us novices, I
yeah,
mean, it's some paraproduction process, which is just a standard quantum field theory
yes,
calculation.
yes,
In some density of material of the star, right, which is
the
well
core
known,
of the star, the core
which
of
is
the star.
which is well understood enough that
Yes,
yeah, yeah.
roughly well understood.
Mhm.
Now, when you start changing so it's in hydrostatic equilibrium, and it's supported by the radiation pressure in the star, and a little bit things depend on opacity and some cross sections to get the exact profile of the star, to see exactly when you start producing these pairs and what exactly will happen after that, right? But not very much. So, so I think there's been several papers of people trying to, as a result of those examples, trying to push this as much as they can, and the conclusion is that it doesn't really want to move. If you want to change one of these cross sections, that you need to move it with respect to the value that you know from experiments by many sigmas. So metallicity doesn't seem to do much. So maybe there's some sort of 10%-ish uncertainty, but all of these events are way above, like at 50 something. That's not something that seems possible. Maybe, I mean, okay, for example, other sources of energy in the center of the star would be able to change this, things like this. But I mean, it's just some dramatic thing anyway, like some sort of, I don't know, dark matter annihilation in the center of the star. You can think of things like this, right?
So
But
it's not one of those things that's contingent like for neutron stars on the equation of state and not knowing that or any of that type of stuff.
I think and this is not at this time. Is that this pair instability happens when the core is still in a normal state, not anything special, and yeah, there is there are some uncertainties in some nuclear cross sections. There is some uncertainty, of course, on what's the amount of heavy elements in the star that might change some opacities and things like this. There are some uncertainties in the opacities, but not enough.
Are the models fully three-dimensional, including turbulence?
I think some of them are, but not probably. No, I mean, with simplification. So usually, I would say some of these things are not fully numerical models, but some. So then the turbulence is included with some prescription. But as far as I understand, as you know, I'm not an expert on this. Not people this is not very sensitive on these assumptions, because the maximum temperature of the star at the core is just something rather robust. And once you start producing these pairs, you're immediately losing a lot of your support into something that is not helping you maintain the star. But this is it's not a new. Okay, but let me just, maybe I should preface by saying that people believe in, as far as I know from not working on this myself, people, both theorists and observers, believe in this pair instability supernovae, and they say super robust. However, there is no example of a supernovae type or something like this where people have been able to associate it. These are pair, this type of supernovae, 1C, B, G, that have this and that. These are the pair instability ones. No. Okay. So I think the belief is that they look very much the same as other type 2s or whatever supernovae. And so in some sense, there is, you can think that observationally, at least, it's not a phenomena that we are super sure about that is happening at this rate and everything, because we see all these examples. I don't think we are in this situation. I think there's always some candidate for an event that should be blah, 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 but then there's some debate. As far as I know, there's no. So maybe it's fair to have, I think one should have some skepticism about this, but I'll just tell you, you know, the story. So people are now faced with these events that clearly violate this, and so at the moment, okay, trying to change the threshold of this pair instability supernova. The heaviest one, 1906. The heaviest one here is super heavy, so I think that's completely out of the question for most people to be able to claim that the pair instability thing is not working at this level. So people think that maybe these guys come from some other population, some other channel, maybe they're secondary black, so they are, you know, themselves produced by the merger of two, like, you know, the secondary event after one of the events that LIGO has seen, you produce black holes that are heavier than that, right? So a lot of the final products of the LIGO mergers are heavier than these, but the rates are difficult because they need to find each other, and anyway, so but maybe these are second generation black holes. Maybe there's, yeah, that's kind of the direction people are thinking about. But of course, they could be primordial, anything, or they, you know, it's a puzzle. So you know, I think we have to be aware that there is a puzzle here. So, but as I was saying, already we had some event that was like this, that was heavier like this, and also the heaviest, the ones that LIGO reported, 170729, which is borderline. I mean, it, you know, depends on where exactly you put the cut, how happy you are about its existence or not, related to this pair instability supernova. Also, for that black hole was let's call it borderline, crossing this threshold for in the LIGO in every analysis, the parameters, but it also had the in the LIGO data release, it had it was like the least significant of all of the events that they published. They claimed that there was a false alarm rate of this not being a real gravitational wave event once every 5 years, something like this. So maybe it wasn't even real, okay? So this gives me this gives me some excuse to tell you a little bit about what we had done. So for us, 170729 was not a borderline. Maybe it was. It's not that we changed the mass or anything, but in terms of its significance, in terms of being a gravitational wave signal, it was not borderline at all. For us, I don't know, once every 60,000 years, less than that could be a fake. And also we had another example, 170718, which was above this. And so we've found an excuse. How come we had different, so we had different list of events than LIGO, and in the context of this, some of them were already, one of them that we had. So let me just use this as an excuse to tell you a little bit about what we had been doing. So let me go through some of these plots. So an example there at the left, top left, is the plot, the curve with a lot of vertical lines is the noise of the LIGO experiment. The y-axis is this is a node plot from observing run 1. The observing run 2 and observing run 3 are basically copies of this curve, but all shifted down, basically, a little bit. And so the y-axis is in log scale. So the noise is shooting up like crazy. Once you go at 20 hertz, it's just crazy high, right? Compared to 100 hertz. The sweet spot for LIGO is 100 to 200 hertz. All the noise has a bunch of very narrow lines with a lot of power. So you have this data with that noise curve. You have some templates of what you think gravitational waves should look like. So you pick some example with some parameters and you convolve the data with that shape to see if at any point the data looks exactly like the template, and then you get a big spike in the, it just sums coherently with all those oscillations, sum coherently with the data, and you get a big signal when you just the specific shape. But you need to try a lot of shapes, but when you try the right shape at the right time, you see some big coherent spike. So if you just go through the data convolving with one of these little filters, examples of which are the ones in the panel there that have, these are from the first the first catalog, you will get an answer which will be some sort of random variable. If you normalize things appropriately, this you will get some answer which is, a Gaussian. If the noise, if the experiment was an ideal experiment, this and the noise was just a Gaussian noise, then you would have the distribution of this score that you get, the value of this overlap would be a Gaussian distribution with unit variance. Say you pick the normalizations correctly, and so you run this through the data, and if in some places you see a huge spike of, I don't know, it then turns out to be 7 sigma or something like that, then you say, oh, I've seen something. Why 7 sigma? Because you're trying so many 7, 8, or 9 sigma. You're trying so many templates, so many examples, and so many different times. These things last. If you shift it by a couple of periods of a few milliseconds, they are just equivalent, like a completely orthogonal thing. So you're trying in these 6 months of data, these templates shifting that each time by a few milliseconds. You have many templates, so you're trying so many things that there's a humongous look elsewhere effect, maybe you would call it, and so you need to get a spike of many sigmas to be happy and say, oh, perhaps this is a gravitational wave. And because you have 2 detectors, you demand that you see this spike in both detectors separated by a time difference that is less than, say, 10 milliseconds, which is the light travel time between the 2 detectors of LIGO. So basically, in the ideal experiment, these results of these convolutions are like this plot here that looks like noise. It's a Gaussian distribution of unit variance. And then when you see these spikes, you're happy, or you detected something. The whole point is that, of course, the LIGO data is not a Gaussian random field. So there's time. So for 2 reasons, or 2 main reasons that we worked on and tried to improve the analysis on. One of them is that every so often the detector produces so-called glitches, which are times when something is off and you get big strains. So examples of so the little plot on the bottom is time frequency at various times. This is from a LIGO paper. You can see these yellow things are just some misbehavior of the experiment. And so if you happen to convolve with when you pass through that specific time, every template that you put in gets a big signal. These are obvious examples that you see by eye, but then you start dialing down the strength of these glitches, and eventually it's difficult for you to see that there's a glitch or not a glitch. But then you can get big departures from this Gaussian distribution for the score if you happen to land on one of these glitches. The other thing that happens is that the noise of the experiment is shifting with time, and this like slow, for the purpose of the gravitational wave detection, is slow changes that maybe happen in a few second time scale for this tens of millisecond, 10 milliseconds event. So during the duration of the event, the noise is a constant, but it's drifting slowly. And so if you don't get this particularly accurately, and you're trying to find events that are 7, 8 sigma, 9 sigma, something like that, it's much easier to get such an excursion, not by the Gaussian random noise, but waiting a time when you just miscalculate the variance of these Gaussian by 10%, 20%, which is the size that we found of these slow drifts. So this creates a big background of events that you think are very high significant just because you had the variance of the Gaussian slightly wrong. And so you need to measure this with this variation on a very fast time scale, which contradicts some of the other things that you want to do, because there's these very narrow lines in the spectrum. And so to resolve these lines in the noise spectrum, to resolve these lines and not broaden them so much that they end up bleeding and creating for you a lot of noise away from the line, you need a big time scale to fit the cosine of the line very accurately and remove it. So okay, there's a bunch of problems like this. So this is what we worked a lot on. And an example of that, so that you can see that this is a very big deal. And it's just, we did it in a different way than LIGO, and as a result, we got different answers. And we think it's better, but okay, fine. But just to give you a sense, so what I will plot there is just the distribution of these so-called the scores that you get when you pass when you convolve the data with these different filters. That's called rho. If it was a Gaussian random field, the distribution of that should be e to the minus rho square over 2 with this just the Gaussian with this convention. And so the plot here are the distributions of the numbers of triggers that we get as a function of rho square. If everything was a perfect Gaussian, it should be like a straight line. Like you see in the top left panel, most of these curves look like a straight line. So that's roughly what you would expect. So there are 4 panels here. Top is the Livingston detector, bottom is the Hanford detector, and the left is for when you're convolving with long waveforms that are corresponding to very light binary black hole binaries, and the more representative ones that are, when you look at the waveforms that are shorter, are that are of the and are corresponding to the masses of all the black holes that LIGO gets, is the right column. So the 2 Livingston Hanford that says BBH 3,0. That's the typical thing for the binary black holes that LIGO is finding. And so if you start, what you see for the distribution of this is this humongous tail that you can see goes up to, signal to noise of rho square 140. Would never be produced by a Gaussian impossible, right? Because the Gaussian would be just a line going straight down. So what is that? And what is showing here is what happens after we apply our pipeline and first try to remove these glitches in some way that, okay, I'm not going to go through, but we spend a lot of time trying to remove these glitches and then trying to calibrate these slow drifts. So that there are 2 curves there when we turn on and off each of these things, and then the green line is the final answer after, and which looks much. Thing to see is that the distribution, if you look at some rho square of 80, signal to noise of 9, or going from 9 or 8, or that's the place where these black holes are being found. You can see that the background after we do our things has changed by many orders of magnitude, right? So, and remember that we are demanding to see things in coincidence. So in each of these detectors, the probability of seeing something is given by these curves. And so we are changing this, the probability that you get for something being real scales like the square of these plots, 1 for each detector, or the product of the top one and the bottom one. So LIGO is doing their own thing, which is trying to mitigate the same problems. We're doing it in a different way, but this is just for you to have in your mind that this non ideal nature of the detector is a very big deal. So the number of triggers that you get after you do your best changes by many orders of magnitude. And as a result, the likelihood that one assigns to a given event can be very different. And so this is an example of, in the case of GW17079, which was the one that LIGO says it was their heaviest one, and they said their false alarm rate is 1 every 5 years for them. And so here in the plot, you can see the location. So this is the value of the signal to noise square in Livingston and Hanford, Y and X axis, we create background by shifting the. So if there is a gravitational wave, you should see something on both detectors separated by less than 10 milliseconds. If you shift the two time stream by much more than that, and you still find something, that is a fake, right? It's just produced by noise. And so we can create background in this way. LIGO does similar. And for us, each of the dark points there is one events gotten in the equivalent of 6,000 years or something like that of background. And you can see there's nobody anywhere near GW 170729. So for us, 170729 has a false alarm rate less than 1 in 20,000 years. So this just to say that, okay, we think we did some better job than LIGO, and as a result, this changed by a lot, but also we found some events, and as an example, an event with also that was already heavy. So this puzzle was kind of already in, for us, it was already in O2. So there's also some events on the low mass cut. I'm running out of time, so I will not discuss the low mass end. So let me just finish by talking about the spin. So I told you a little bit about the questions about the mass of the black holes and how come they are so heavy, and there's also some examples in this low mass gap. But then there's the question of how these black holes came together to form a binary before they merged by gravitational waves. And the puzzle there is that the separation between the two black holes that is needed for them to merge by gravitational radiation in the age of the universe is significantly smaller than the size of the stars when they go through these massive stars when they go through their giant phase. So obviously, if you start with a binary, they had to be separated by more than that, by more than the distance needed for them to merge by gravitational radiation. But on the other hand, you see these binaries merging. So how did these two black holes find themselves? And so there's two competing mechanisms that people have thought about. One is in which there is a binary. These two stars start, far away because they're separated by more than the sizes of the stars. But then, first one goes supernovae. Eventually, the second one becomes a giant. It engulfs the first black hole. This black hole is sitting inside of the envelope of the second star. It drifts towards the center, and for some reason it stops right before crashing to the center, and you end up with a binary, and the core of the energy of the falling black hole is enough to unbind the envelope of the second star. So you end up with the core of the second star and the black hole of the first star, and then the black hole of the first star. The second star goes supernovae, and you end up with the binary. So it's a whole complicated story with a lot of messy astrophysics, which, okay. But we know this happens out there. We see these common envelopes in some other systems. And so I think this channel is the classical channel. Other people like more the situation in which the two black holes form separately in a sufficiently high density environment, like a globular cluster or something like that, the center of a galaxy, in which there's enough stars that the two black holes and another star can, you form the two black holes separate, and they find each other and they scatter with each other. Maybe they scatter in a three-body interaction, and they become bound, and all these scatterings eventually lead to exchanges between black holes and stars, and blah blah, until and also this eventually this binary starts losing energy by giving it to third bodies, which is scattering, and it shrinks its separation, and you form the binary in a dynamical way. At the current time, we're trying to disentangle which of these two channels is the main channel, and the way to do so that people have been thinking about is to use the spins of the black holes, because in the case of the binary stars, the tides from the black hole on the core of the second star can be large enough. Also, they form in a binary, so the tides can the spins of the black holes are related, are coming from the orbital angular momentum of the binary ultimately, and so more or less they should lie on the same direction as the orbital angular momentum. The spins and the orbit angular momentum should be aligned, except for, you know, when you get these super explosions perhaps, or when in the formation of the black hole, maybe if there is a little bit of mass loss, there's a kick to this black hole, and maybe that changes the orbit by a little bit. But especially the second black hole, the orbit is already too tight to be perturbed in any meaningful way. So channel number one, you expect the black holes spins to be aligned with the orbit. In the channel number two, the two black holes form independently by the and their spins and the orbit of the final binary are not related to one another, and so the spins should be random. And so what's the situation with the last thing I would say? What's the situation with the measurements of the spin? So here there's various plots of all of the events, or at least the ones that are, you know, uncontroversial events in the LIGO 01, 02, and 03. So very high significant black holes. So this measurement of the sky effective in various ways of plotting it, this component of the spin in the direction of the angular momentum. So let's just look at the panel in the left. That one shows the measured value of chi effective for various for all the various events, divided by the error bar with which you can detect it. And so given the number of events, if all the spins were zero, you would never expect more than a 2 sigma event. There are several events that have spin detected with significance more than 2 sigma. So clearly we are seeing spins in the black holes. But the second thing to notice in this plot, that all the ones that are significant in their spin have positive values of this chi effective. So they are aligned with the so positive value means the spins of the black holes are aligned with the orbital angular momentum, as opposed to in the case of a Gaussian, of a random distribution, there would be similar amounts on both the left and the right side of this line. So there is some indication, I think, already that the channel where the things form together in a binary is playing a significant role. I mean, if you try to quantify this, I don't think we can be sure at the many sigma level, but there is some indication of that. And so that's, yeah.
What is the sigma, or what is the variance of the spin?
So this is very much depends on the, so you can see on the second plot, for example, I plot the actual value of the spin, and the error bar is the little, so each of them has a different measured spin. The error bar is different for each of them, because the longer the event, for example, the more cycles you have, the lighter it is, you can measure it better. So you can see in the middle panel, you will see a bunch of events which are not consistent with zero spin, which are the ones that you can also see on the right, say more than 2 sigma. You will also see that the sky effective, the amount of the spin is not very high. So it's still the case that they are spinning rather slowly. So for example, if one of them is maximally spinning, the typical mass ratio of these guys is around 1, and so you would expect a chi effect, maximal spinning in the direction of the angular momentum. The value of this chi effective is 1/2. And so there are some of them that are like that they're like 1/2, but there are several of them which are detected with smallish spins. You can see them at the, around the number 20 or something. You see a bunch of them with relatively good measurements away from 0, away from 0.5. So I think we detect the events. We detect spins, or LIGO detects spins. They are preferentially aligned with the orbit. They are not necessarily particularly high. There are several examples in which you can conclude that it's none of the two guys are maximally spinning. They have to have, there is some spin, but both of them are not maximal. It's not possible to have them, either of them, I guess, maybe better. Neither of them is maximally spinning, neither of the two black holes. So they have some intermediate spin. So again, this is not something easy to understand, I think, at the moment. So I run out of time. So let me stop here. So I'd say, let me summarize by saying that LIGO has produced many events. They have led to quite a few astrophysical puzzles. The masses, there are several examples with masses above this maximum. So maybe one thing, let me just say before, is that something is happening in this threshold of the pair instability supernovae, because although I emphasize the fact that there are several examples heavier than that, they are a small fraction. So if you just continue the population that you see below that and you extrapolate, say, with a power law, you would expect many more. So clearly there's some transition happening at these 40 solar masses. There's a decrease in the number, but there's still some. Maybe that's a good summary of what's happening. We don't know if this how they are produced, if there's something wrong with our understanding of the pair instability, of these are second generation black holes, or they're black holes that are born in some very dense environment like the center of the galaxy, and they are accreting a lot, or in the disk, in some disk around the supermassive black hole. Something happening that we are still need to sort out. One option to sort this out is through the spin. At the moment, the measurement of the spin is not great, but you can still see that the events seem to point to spin aligned with the orbit. Whenever we can see the spin, whenever we can measure a spin that is, with a good inconsistent with 0, it's on the positive side, but not particularly large. And so this also again presents some puzzles for the origin of this spin. So this is where we are at. They will release the O3 half of the full data of O3. We will do our analysis there. Hopefully we will find some more events, and we will reassess the significance of the events that they had. Maybe they have several of these borderline events that we might have a different opinion on how significant they are. And there is the second half of O3, which the data was already taken, and they will eventually announce and also give out. So in the near, not so distant future, there will be hopefully, if we can find twice as many events like in O2, there will be 4 times the total events that we have now. Okay, so let me stop there.
Okay, let's thank Matias and ask questions.
Yeah, hi, Matias. I want to understand a bit this small spin puzzle, how important it is, and whether it's important enough to think of BSM mechanisms for this spin reduction, like black hole superradial.
Mm-hmm. So, okay, so for me, it's a little bit of a puzzle for the following reason. So if you think of this, so let's think right before we have the black hole binary. We have a core of a star, and we have the black hole, the first black hole. First of all, just to be clear to everybody, from the point of view of a star, maximally, the A of 1 corresponds to maximal spin. That amount of angular momentum means nothing. This thing is super big. It can easily have much more angular momentum than A equals to 1. So that's not a particularly special point, okay? And then you can ask the question, if you are tidally locked like the Earth and the Moon, what kind of angular momentum you end up giving what angular momentum does this core star get? And you can easily see that for a lot of distances is much larger than the amount of angular momentum needed to create a black hole that is maximally spinning. And the second thing is that the transition distance for which you are able to tidally lock and give this the core of the star enough angular momentum to be a black hole that is maximally spinning is comparable to the distance that is required for the system to within a factor of 2 of the distance that is needed for the two black holes to merge by gravitational radiation in the age of the universe. So you would think that naively you would have examples of systems in which the black hole is a little bit too far to be to tidally lock the star, or a little bit too close and it will tidally lock, and then the spin will be, the angular momentum in this core is much larger than what so you will have a lot of angular momentum, and naively you would expect a black hole with maximal spin. So that's the reason why it's a puzzle. Now, I think it's fun to think about various scenarios. The most probably, I suppose the most likely thing is some sort of astrophysical explanation, some mass laws that carries away some angular momentum or something like that. Yeah, so that's the situation.
Is there any correlation between spin and the mass?
At the current time, when I look at this data, I see things, but it couldn't be imagining. So because the error bars are big, so it looks like it looks like, for example, the heaviest of the black holes are all spinning, or are all ones in which, so the top of this plot, most of them, of this chi-effective plot in this slide, they are the heaviest ones. But there's only a few of them, and so I don't know. I oscillate, and also they are the ones that for which the error bars on everything are kind of largest, because they are heavy. They only have a few cycles in the LIGO band, and so these fits for the parameters are perhaps the most difficult. But there is such a thing. There appears to be apparent correlation, perhaps. I mean, you maybe see it by eye. I don't have a plot here, but you can also, it's not significant enough that you cannot convince yourself that you're imagining it. So yeah, I don't know. At the moment, I would say we don't see any that I can tell you, yeah, go for it. But I think also, for example, in this plot, I'm putting every event, but clearly the masses change by a big factor, right? From factors of maybe even 10 of these black holes. And so, and we are already seeing some other special events where there is most of them have mass ratio of order 1, but there are some few of them that have mass ratios very different from 1. So I think with time we will start seeing different groups, and it's like the standard astronomy thing that they will start complicating the picture. So maybe at this point something more clear will emerge.
What is this? There's selection effects here, right? How do those go with mass? Or I mean, you were explaining that you know, you don't see as much of the time curve of the massive ones, for one thing.
Yes, there are significant selection effects. For example, in terms of the mass, obviously the heavier ones, yes, they last shorter amount of cycles, but they are also much brighter, and so in total you can see them much further out. There is that. So for example, if you want to infer the distribution of masses out there in the binaries compared to the distribution of observed masses, is completely different. So while the distribution of masses probably is some sort of power law that goes with m to the -2 or something like that, these guys are more equal in log, like the observed ones are more like equal in log. So there is a big selection effect. In terms of the spin, there is a selection effect. You can see guys with positive chi effective to a little bit further out than, and so you might think that a little bit of these, so of course we know this, and when I'm telling you, I've already taken this into account, but a little bit of the fact that, so you might expect to see more with positive chi effective than negative chi effective, even if the distribution was perfectly symmetric, but we see it's not that effect is not enough, especially because that gets like a very strong effect when things are very highly spinning, but as you like chi effectives of order 1, but most of these guys the effect is very small, like a few percent or something. Difference in the volume up to which you can see them. If it's say if the chi effective is 0.1 plus or minus 0.1, the difference in the volume is a few percent, so that's not a big deal. By the time you get to 1, then the maybe a chi effective of 1, then it's a much bigger effect, and then you have to be more careful. But of course, we take this into account when we try to do more quantitative.
Oh, can I ask you again about the small spin? At what, as we collect more and more data, and we understand we understand the values of the spin and mass better and better, will we reach a point where we can exclude standard model explanations like mass loss?
Will we reach a point? I haven't thought about this. I think it might depend also on the absolute value of the spin that we are talking about. I think if we end up only with very small, I mean, different from 0, but very small spins, getting rid of that amount of angular momentum might be easier than if we are talking about, well, I guess, yeah, if we're talking about something that started spinning maximally. So yeah, I think, I don't know the answer to this question at the moment. I think it will take a little bit of time, and it will take being able to separate also the other components of the spin, which I'm not plotting here because the constraints are not very good, but I think if we start seeing if the spin has components in the plane, and we will start to understand things a little bit more, but I think it'll take some time.
Can I ask, is measuring the eccentricity, maybe perhaps at slightly lower frequencies, for example, is that useful? Do you think there's a use to that?
I think it's very useful because in many of these dynamical scenarios, of captures and three-body interactions, or maybe the binary is itself has a third body that is making it change its secular, evolve the orbits, and to be able to get them close enough eventually to merge by gravitational radiation. In many of these examples, you end up with significant eccentricity, and there's been a lot of work on this. In practice, when you it's kind of an unfortunate situation. I mean, the eccentricity drops if you start with an eccentric orbit. That decays by gravitational radiation pretty fast, and so given the minimum frequency that LIGO sees, and the fact that it's just seeing the very end of the merger, for most of the phase space of capture radius of the orbit and or semi-major axis and eccentricity, it would have decayed by the time it gets to the LIGO band. But it's not 100%. So there should be some percentage events that might have some detectable eccentricity. It makes a huge difference if you can start at 10 hertz versus 20 hertz, and as you saw, the LIGO noise is going up like crazy. So improvements in this low density might improve the numbers that you could see, or eventually something like LISA or something like that goes to lower frequency. This will be very interesting, very useful. There's a lot of work on that, on the theory side of how to predict these eccentricities in the different scenarios. And also, if you start talking about things that are significantly eccentric in the band of the gravity, so if it's a small perturbation, we know how to search for it if the eccentricity is very small. But if we're talking about large eccentricity, the templates, I don't think we have them, becomes a problem. So that's also another area that needs work. Maybe it's not urgent given the frequency, minimum frequency of LIGO, but it's also very interesting.
Yeah, thanks. And would these formation scenarios, would getting down to hertz or 10 to the minus 2 hertz, millihertz, is that, I mean, are you getting into regions where you really would expect large eccentricity?
Yes. I mean, of course, it depends on the formation scenario. If it's just the binary evolution, maybe not so much. Although if most of these stars, so there is this observational fact that most massive stars are in binaries or triples or quadruples, so in systems with others. And so, if some of these systems have a third companion, so that can excite eccentricity. So yeah, I think not even so, 1 or 2 orders of magnitude in frequency is very good, very, very good at this kind of sensitivity.
Thanks. Yeah, great.
Quick naive question.
Yeah.
What in these very massive progenitors of these black holes, what core temperature are actually we talking about typically?
Well, you need to be able to produce pairs, right? So
it's MEV or?
Well, I guess the tail of the
tail. Yeah, that's really what I'm asking, I think.
Yeah. So I don't know the temperature of the top of my head, but yeah.
Okay. Thank you.
So Matias, could it be that some of these events are not independent events, but instead images of the lens images of the same lens event?
Thank you. Okay, so of course, like anything else on the sky, gravitational waves are also eventually we will find examples of lenses just as supernova. But or galaxies. Now the cross section for lensing, as you know, is pretty low. So if we think about the fraction of all quasars that are lensed or galaxies, that is a small number. So you don't expect naively, or you don't expect to see, with the small number of events so far, to see a gravitational wave event, a gravitationally lensed event of a gravitational wave, unless some very, I mean, people try to push the numbers radically, like George Smoot, or whatever. If the things are so, if for example, just there is no, in the local universe, there's no events whatsoever, and they're all being produced at super high redshift, and the only way you would find them is if they are gravitationally lensed because of the magnification, then you can try to come up with some scenario like this in which everything is super magnified. But then anyway, it just doesn't work out too easily, or at all, probably. However, when we search for lens events ourselves in the data, and we found some candidate events that have the same parameters from the same location on the sky, with a time delay that made some sense for a cluster lens. And also interestingly, in the case of in a gravitational lens, so the images are the extrema of the time delay. So you can compute for different paths from the source to the observer, the time delay, and the images are the extrema on the surface of the time delay. And so it can be a maximum, a minimum, or a saddle point. So these are the places of the time delay surface where you form images. And these have different parities. So it turns out that in the case of gravitational waves, you're measuring also the phase of the wave. And so it turns out that when you, so there's a discrete phase shift that in some convention, let's call it pi, when you are a saddle point with respect to one of the other. So if you're an odd image, and so first of all, these images that we found were had not only the same parameters, but also the correct phasing, and also one including this phase shift of the saddle point, and furthermore, we said, okay, given that, so these were some examples in the existing catalog, but then if you know the position on the sky and you know the parameters and so on, you have a much smaller look elsewhere effect, and so you can say, let me search a little bit deeper into the data to see if I see another image, and we found another image. So we have a paper with all of these. So if you start multiplying all these probabilities, it's just crazy that you've seen all these coincidences. But also the gravitational wave hypothesis is crazy. So I have no explanation for this. So unfortunately, yeah, that's the situation. There is some candidate gravitational wave that unfortunately or fortunately we found somehow, and I don't know what to make of it because you don't expect it. So I don't know.
Are those all in O1 and O2?
Yeah.
Did you look in O3 as well? Or?
We don't have the data, so I don't think any of these events it's another image of the ones that, so we could look, if once we have all the data, we could try to look. I mean, of course, there's 2 years passed by, and so the time delay starts maybe becoming complicated. But we will look probably when we have the data. But I don't think any of the events that they reported could be another image of the ones that we have. I don't know what to make of it. So probably just a coin. I forget now the chances, but 1 in 10,000 or something ridiculous. I mean, but also lensing is also ridiculous. So I don't know. It's just crazy. I stopped thinking about it because I started thinking all kind of crazy things, like maybe maybe these are near a supermassive black hole, and you see the various images, or some cosmic string. I don't know. I couldn't make anything work out. So anyhow.
Okay. Any other questions for Matias? Okay, if not, then let's thank Matias again for a very
Okay.
nice talk.
Thank you. Thanks for the invitation. See you guys later. Bye bye.
Yeah.